Alright, in the last video we saw we were able to manipulate matrix equations. So something like ax plus b, we were able to find x, right? But how do we solve for it here? Well, I mean, normally, right, you would do x is equal to b over a, but the question is, how do you define dividing by a matrix, right? The idea here that we actually want to do instead is not matrix division, but when we divide, right, that's the inverse operation to multiplication. So, and similarly, subtraction is the inverse operation to addition. So instead, can we think about this idea of an inverse or undoing what we did in a different way? Okay, and that's where we can think about this concept of inverse and then remember the definition of multiplicative inverse, okay, because that's ultimately what we want to do. We want to undo the multiplication. We want to do the inverse operation multiplication. So if we have an n by n squared matrix, if we have a matrix that we call A inverse, that's how we say that -1 thing, A inverse, if we do A times A inverse and we get out the identity matrix, and then it's also in either order, and well, not in either, in both orders, I should say, then we can say that A inverse is the multiplicative inverse. So if we're wanting to check to see if we have inverse matrices, we need to check the two orders. So we need to check AB and we need to check BA in this case. And if they're both equal to the identity matrix of order 2 by 2, then we would say that they are inverses. Okay, so if we do the matrix multiplication of AB, so again, I'm doing row times column and then moving on from there. So I get 40 minus 39, that's 1. And then, let's see, then moving on to the second column. So -12 plus 12 is 0. And okay, this is boding well, okay. And then sure enough, you get 0 and 1 out. Okay, so this is looking good, but I do need to check the other order as well. Okay, so let's check BA. So now I'm doing row of B times column of A. So again, I'd have 40 minus 39, that's 1, and then, let's see, now column 2, and yep, that's 0, and then 0 and 1. Okay, so I'm going to say yes, since they are both the identity matrix of order 2 by 2, I'm going to say yes, A and B are inverses. Okay, so inverses. So certainly remember the definition of multiplicative inverses, but ultimately we want not just to verify like things are inverses, we want to be able to find them. And so here is kind of the process we're going to use. Okay, Gauss-Jordan elimination does pop up. Okay, what we're going to do is take a given matrix and we're going to append the identity matrix of that same order to the other side. Okay, and I should also mention that these matrices have to be square. Okay, they have to be square. You can't do this with a matrix that is not square. Okay, what we're going to do is with the matrix and that identity matrix appended onto it, we're going to do row operations so that the identity matrix shifts from the right side to the left side. Okay, this is a really Gauss-Jordan elimination. Okay, since we're in a square matrix. And then when we get a matrix on the other side of this appended part, so the identity now becomes this other matrix, that's our A inverse. Okay, so here in this example, we want to find B inverse. So what I'm going to do is I'm going to start with 9, 7, 5, 4, and then I'm going to append to this 1, 0, 0, 1. Okay, this was a 2 by 2 matrix, so I append I2. Okay, now I just have to do row operations. Okay, so this unfortunately is not going to be pretty. We're going to do our best and persevere. Alright, so I'm going to do 1/9 of row 1, put that into row 1, and at the same time I'm going to do 5 row 1 minus 9 row 2 and put that into row 2. Okay, and when I do that, I obtain, let's see, so it'll be 1 7/9, 1 over 9, and 0. Okay, and so then that would be 45 minus 45 is 0. Now 5, so 35. 35 minus 40, or 36 is minus 1. And then 5 row 1, so that's 5 minus 0 is 5. And then, let's see, I have a negative 9 here. Okay, first row is a little ugly. We'll deal with it. Okay, so now I would just do negative row 2 into row 2. And then I will have it in, this will be Gaussian elimination form, or what I would get after Gaussian elimination, or row echelon form. So 7/9, 1/9, 0, minus 5, and then positive 9, 0, 1. Okay, but now I want to knock this 7/9 out, so I'm going to do minus 7/9 row 2 into plus row 1 into row 1. Okay, and so I get 0 1, or 1 0 0 1. Okay, there's my identity matrix. Last row stays the same. Okay, but now I need to do negative 7/9. So I'd have positive 35/9, and then I add to it 1/9, which is 4, miraculously, and then I would take negative 7/9 of row 2, so that'd be negative 7, and then add that here, so I just get negative 7 there. Okay, so now this is in the form that I want. This is, I2, which was over on the right to begin with. It's over on the left now, and here was my matrix B, so that means that B inverse is this nice matrix here. So I'm just going to say B inverse is the matrix 4 minus 5 minus 7 and 9. Okay, so in this case we were able to do Gauss-Jordan elimination to get our matrix here. Okay, if in the event you're doing the row operations and something just doesn't work out, like this identity doesn't pop out, or you get a row of all zeros, then we would call the matrix singular, meaning that the inverse doesn't exist. Okay, so singular inverse matrix doesn't exist, and then consequently if it does exist we would say it's non-singular. So for our example that we did, we would say that matrix B is non-singular. Okay, so here's one example, and we'll get some more practice with a couple more examples in the next video.